Okay, let's do this here. Okay, so if I divide, what's the highest power going to be? X. So it's going to be limit x approaches infinity. 3x plus 2 over x over 1. Can I go to that step? Is that okay? Anything math rules there? Okay. Good. So I'm going to evaluate in for infinity. So it's going to be equals 3 infinity plus 2 over infinity all over 1. What's 3 times infinity equal to? Good. What's 2 divided by infinity equal to? We don't mind infinity. Infinity is okay for a number, right? I think it just all means that this is like a parabola. It's not a parabola, okay, right? If you think about how a parabola goes, it's going off. Okay, good. That should be able to take you through your assignment, I believe, with those 3 pieces of information. Okay. All right, today's lesson is called continuity. This is going to be fast. This is going to be fast. We're going to say a function f of x is continuous at x equals a if and only if the limit as x approaches a f of x equals a. Okay, so basically, oops, not f a. Basically what that means is in order to take derivatives, remember we said yesterday or 2 days ago, the function has to be continuous. So what a continuous graph means is like 99% of the graphs you've seen in your life, including in this course. When you get to calculus next year, it won't be the case because that's whenever people come back to me and they say, what should I change about this course? They should say, talk about continuity. It's so important in university. In high school, it's not important at all. Okay. So basically, sorry, did I say that? Was I too mean that? Okay, it's not important in high school. Okay, but in university, it definitely is. So we're going to say, so for a function to be continuous at x equals a, number 1, the limit x approaches a f of x exists. Number 2, f of a is defined. Number 3, the limit x approaches a f of x is equal to f of a. You're probably saying, what the heck does all that stuff mean? I'm going to show you with pictures here for the rest of today's class. Okay. Basically, there are some graphs that you can't take the derivative at a specific point because no point exists or weird things happen around it. Okay. So basically, if you have a nice graph like this, you have no problems taking the derivative at any point. But if you have graphs when this stuff starts happening, or this stuff starts happening, or this stuff starts happening, there's going to be problems taking the derivatives at an asymptote. Just one example, okay? So I'll erase that. You don't have to copy that down. Okay? That's tan graph. That is okay. But those are some graphs that there will be problems when you can't. There's not a point exists. How to take the derivative. The other one will be one like this. I'll draw these in a sec. Okay. What's the slope going to be at that point where it changes? Well, we don't know. Okay. So I'll deal with that right now. Okay, luckily we don't get into most of those things in this course, okay? So we're going to say graphs of continuity and discontinuity. We're going to say a graph is continuous if it can be drawn without lifting your pencil. Okay, so every polynomial graph will be continuous. Put your phone away, please. Every sine and cos graph will also be continuous. All right, every exponential graph will be continuous. Okay, so any graph where you can just sort of draw without lifting your pencil is going to be continuous. An example of that. We're going to say x cubed is continuous. And any derivation of x cubed is going to look something like this. If I take a look, I'm going to take my pencil, I'm going to do this. I'm going to draw the entire thing without lifting the graph. That's continuous. There are no points that will make it, that will cause problems for it. And you guys spent a whole 5 months doing x cubed last semester, right? 1 month doing it anyway. 1 month for fun. You never seen x cubed before, ever? Yeah. You spent a month doing it, didn't you? Wasn't 1 year on polynomial graphs last month? I shouldn't be so specific. Okay. Example 2 is asymptotes. We're going to say a rational function the simplified form has vertical asymptotes. And that's non-continuous. At the zeros of the denominator. Okay, so let's say my graph is f of x equals 1 over x plus 1. Okay, the problem with this is, where is the issue going to be on that graph? Where is this going to be discontinuous? Yeah. Okay, so we're going to say here x can't be negative 1. So f of negative 1 doesn't exist. So that's going to fail our second point there. If you want the graph of 1 over x plus 1, it looks something like this. Think back to grade 11 when we did this. Okay, so the derivative wouldn't exist at that point. And again, most of the graphs we're going to deal with in high school will be, this won't be a major issue, in university it will be a major issue. So that's a big jump between high school and university. Are you okay on the logic here of what I'm doing here as well? Right? If the point doesn't exist, then you can't find the slope at that point. All right, here we go. Example 3. Sorry, now I'm going through quickly because I want to finish this up. It's a whole.
Should that be f of negative 1 or f prime of negative 1?
Oh, so, well, f of negative 1 doesn't exist, and also f prime. As far as the continuity you need the point to actually exist as well, right? So since the point doesn't exist, so here we go. Example 3 is whole. So this, I'm going to use the same example I used. Okay. That's my original function. So if you take a look at that, that's going to be the equation. It's going to look something like this. X can't be negative 3, or something like this, right? Was the graph that we did at the beginning of the year? Is that right? Something like that, right? Okay, so where does it look like from my graph there's going to be problems? Okay, we'll probably get that giant hole. Okay, so we discontinuous at the giant hole. Okay, now for the reason that is, okay, so we're going to say, we can look for this. What I'm basically checking for here is if the limit of x approaches a f of x equals f of a. That's sort of what I'm dealing with here, okay? The problem is with this, the limit's going to exist for this, but the point doesn't actually exist. So the limit for this, when I sub it, I'm going to factor and call this x plus 3 and x minus 3. That equals 6. What happened there? Is that right? Did you make a mistake there? So that equals 6. Okay. So the problem is here, the limit exists. So the limit as x approaches 3 of f of x has to equal f of a. Well, the limit equals 6. This is undefined. Okay, so as those two.
If the limit of x is 3, shouldn't be shown the dot at 3, not negative?
I was thinking that as I drew my graph that something's wrong there. So this one, thank you. This is a diagram we drew on the first day of the year. We did that one. Okay, sorry, yeah, sorry. It should actually look something like this. Sorry, thank you. Right, something more like that would be better. Okay, so all we're saying for the logic here is if the point doesn't exist, that's all. That's basically the logic I want to do right here. And I want to do, this is actually, next one's going to be jump discontinuity, then I'll stop, okay? Example 4 is going to be jump discontinuity. And you probably haven't seen this since grade 9 EQAO. Okay, what jump discontinuity is this? It's going to be a graph that looks sort of like this. That would be jump discontinuity. Okay. So what it means is basically graph in pieces. Okay, so it's going to look like, sorry with that. So let's pretend this is f of x, and we'll deal with these a lot more in university, okay? It's going to equal x if x is less than 3, and it's going to equal negative x squared if x is greater than or equal to 3. Okay, so that's sort of what, you'll see a lot more of these in first year university for equations, but I don't do any of these in this course. Okay. Except for tonight's homework, that's it. After that, I won't see you again. Why am I saying that? I don't know why. It's because when John Stegmeyer comes in here next week, he said he wants to come in and tell me all about his first university. And the first thing he's going to say to me is, should I have more discontinuity in their courses?
We didn't have that in my class, did we?
All right, that's it. Homework, and then we're going to stop. If you guys want to work on your choice assignments for the rest of the period, you may. There we go. As far as your test goes, there'll be a 1-mark question on continuity. That's it. Okay, so there's a one